let's look at how we can use the concept of compound interest to motivate the exponential function. So this is going to be the exponential function, and I'm going to put exp of z because we'll look at the complex case as well as the real case. So suppose your bank gives you an interest rate of X per annum. X might be 5%, say. So if you had $1,000, after 1 year, you've now got your original $1,000 plus X times that amount. i.e. 1 plus X times the original amount. So you can see that after 3 years, we've now got 1 plus X cubed times our original amount. For example. So what if the bank, instead of calculating the interest every year, were to calculate it every month? So now it's 1 plus X over 12 to the power of number of months in a year, i.e. 12. So now suppose the bank compounds the interest every day. So now you've got 1 plus X over 365, and it's being done 365 times a year. So the question is, are we heading somewhere with this? As you increase n, what's happening to 1 plus X over n to the power of n? Limit as n tends to infinity. What's that? How much money do you get back after a year from your original $1,000 if the bank is continuously compounding your interest? And the answer, amazingly, is the exponential function, exp of x, otherwise known as e to the x. And we've looked at this function before. We can define it as a power series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... And it looks like this. X with 0 is 1. Anything to the 0 is 1. Now let's see if we can make sense of this result geometrically. So if you have some function and you know its value at a given x, and you wish to know its value at, say, x plus h, then you can say f of x plus h is approximately equal to f of x plus h f dash of x. This is known as linear approximation. Basically, it's saying as you zoom in closer and closer onto this point, this function looks more and more like a straight line, and so you can use that straight line to better and better approximate the function as you approach x. And this is the equation for that straight line. Yeah, we have a slope, and this slope says if we go along 1, we go up by f dash at x. But we're not going along 1, we're going along h. So how much do we go up? Well, just h times f dash of x, and scale both the x and the y by h. And that takes us to that point there. So applying that to our exponential function, we have exp of x plus h is approximately equal to exp x plus h exp dash at x. But the exponential function has this property that the derivative is the same as the function. So exp dash is the same as exp. So we've got exp x plus h exp x, which is exp x 1 plus h. So we can say exp of delta is roughly equal to exp of naught 1 plus delta, which is just 1 plus delta, and exp of 2 delta is exp of delta plus delta, and you can continue etc. So if I take my x value and I cut it into n strips, so here n equals 4, and the width here, our delta in this case, is going to be x over 4, but in general it's equal to x over n. Then this value is going to be approximately 1 plus x over 4, and this is going to be approximately 1 plus x over 4 squared, then 1 plus x over 4 cubed, then 1 plus x over 4 to the 4. So we have exp x is roughly equal to 1 plus x over n to the power of n. And that becomes a better and better approximation as n tends to infinity. Now it's good to start with this geometric argument because it means you can see the result intuitively just looking at it on paper. I'm not sure whether it formalizes nicely though. we can work formally and show that this becomes ultimately equal to the power series. So let's have a go at that. So we're trying to show that 1 plus x over n to the n approaches that power series. 1 plus x over n to the n using binomial expansion, aka Pascal's triangle. So we've got 1 plus n choose 1 x over n plus n choose 2 x over n squared plus dot 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 all the way to n choose n, which is 1 x over n to the n. Which is equal to 1 plus n choose 1 is n. There's n ways of choosing one object out of n objects. So you've got n lots of these, so it's just x plus well, let's look at the kth term. It's going to be n choose k, so n factorial over k factorial n minus k factorial times x over n to the k plus dot 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 plus x over n to the n. And to be consistent, I should make this the kth term here as well. So tidying this up, we've got 1 plus x plus da 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 plus. Well, let's look at what we're aiming for. What we want for this kth term is x to the k over k factorial. So we've kind of got that there and that there. So let's bring them out. X to the k over k factorial times n factorial over n minus k factorial is just n minus k plus 1 times n minus k plus 2 times dot 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 all the way up to n. And there's going to be how many terms here? Well, we could think of this as n minus bracket k minus 1 and this n minus 0. So from 0 to k minus 1 it's just k elements. So there's k of these and work going over n to the k. So we could just put each one of them over n. So rewriting these terms, we could divide through, and this is now 1 minus k minus 1 over n and the next one will be 1 minus k minus 2 over n, and so on up to 1 minus zero over n. So from here it should be fairly obvious intuitively that it works. For example, you're interested in the first 1,000 terms of this series, so you're interested in k going up to say 1,000, and then you just let n spiral out to infinity, and these contributions are going to get smaller and smaller, arbitrarily small. So this is how we would build a formal proof. We would say that because 1 plus x plus da 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 plus x to the k over k factorial, as you keep adding on terms, this converges to exp of x. So if you want a particular precision, say you choose some epsilon and you want to be within epsilon of that exp of x, there's going to be an associated k that you have to go to, and any contribution beyond the kth term, the sum of those contributions is going to be less than epsilon. So we could say choose epsilon greater than 0, and now there exists some k0 such that the first k0 terms are within epsilon of exp x. So we wish our series to be within epsilon of the correct result. That means we need the first k0 terms of the series. And that means the rest of the terms have magnitude less than epsilon. So our plan of attack is this. We're going to show there exists some n0 such that for all n greater than n0, the first k0 terms of this binomial expansion are within epsilon of the first k0 terms of the exponential series. And we would also need to show that the remainder of the terms from k0 plus 1 to infinity has magnitude less than epsilon. This expansion as n tends to infinity is within 3 epsilon of the series, because the series is within epsilon of the series up to k0, and the series up to k0 is within epsilon of the binomial expansion series up to k0, and the binomial expansion series up to k0 is within epsilon of the binomial expansion with all terms. Notice I've used big pi notation for the product of all of these factors, just to save writing. Maybe I should put that x to the k over k factorial. And so this is our kth term of our binomial expansion, which is equal to x to the k over k factorial big pi, just as sigma is sum, pi is product, s for sum, p for product, between 0 and k minus 1 of 1 minus L over N. Now that's the hard work done. What remains is tidying up, basically. It's obvious that this product, as n approaches infinity, tends to 1. It gets arbitrarily close to 1. So this first step should be easy to do. By choosing your n0 large enough, you can replace this pi product with, say, 0.999999, as close to 1 as you like. Proving that the rest of the terms have a size less than epsilon is also trivial, because this pi product is less than 1. It's tending to 1 from below. So each term is less, slightly less than x to the k over k factorial, and we know that the sum of the remainder terms of the power series for x is less than epsilon. We've got that here. We carefully chose a k0 such that the first k0 terms are within epsilon of the desired value. Therefore the remainder terms from k plus 1, k0 plus 1 to infinity are going to be less than epsilon in size. So this is true. Previously this was true, and this is true. So therefore 1 plus x over n to the n is within three epsilon of the sum to infinity x to the k over k factorial. For n greater than n0. Done. Also, I could leave this as an exercise to prove these two steps thoroughly. Again, it's not too difficult, but it uses up paper, and I don't have too much left, and I wish to still look at the complex case, where x might be a complex number. Okay, due to my iPhone messing up the recording of this last section, rather than rub it out and rewrite it, I'm just going to walk you through it. So naturally we would like to extend this compound interest definition of the exponential function to the complex numbers. And it turns out we can do this no problem. The limit of this approaches the power series for x z. But the useful thing of having it in this form is it gives us geometric insight. Just as this real case gave us geometric insight, we can do the same for the complex case. So what does this mean? Well, say n equals 3, then we're looking at 1 plus z over 3 cubed. So here's z. Z over 3 will be in the same direction, just a third as long. So there's 1 plus z over 3. And when you cube a complex number, the angle triples and the length cubes. So this is a bit more than 1, so this will be a bit longer, and this will be a bit longer still. So there's 1 plus z over 3 cubed. And as we increase n, this is going to approach a certain point, which, as we're going to show, is actually e to the x at an angle of y. So this becomes 1 plus a little thing, let's call it epsilon. And using this picture, we can see that 1 plus epsilon is roughly equal, if you write it in polar notation, to 1 plus the real part of epsilon at an angle of the imaginary part of epsilon. So here's the real part of epsilon, here's the imaginary part of epsilon. You can see that as the length of this vector dwindles to 0, we get closer and closer to the x-axis. This vertical line approaches this arc length. And the arc length on the unit circle is just the angle in radians. So we have the imaginary part of epsilon as the angle, and also the radius approaches 1 plus this horizontal segment, which is the real part of epsilon. So you can see I've marked off this approaches 1 plus the real part of epsilon. So I have this approximation. Now if I want to write epsilon back as z over n and raise it to the nth power, I've just got this thing to the nth power, and when you raise to the polar complex number in polar form to the nth power, the angles, you multiply the angle by n and you raise the radius to the nth power. Notice I can write the real part of z over n as the real part of z over n, and the same for the imaginary part. Yeah, here I've got n times the imaginary part of z over n, and the n's are cancelling. And this, as we showed above, is just exp of the real part of z. Now maybe it makes it tidier to write z as x plus jy, then as n tends to infinity, 1 plus z over n to the n approaches e to the x at an angle y. Notice that Euler's identity just comes out as a special case where x is 0. So if z is a purely imaginary number, its real part is 0. So we're looking at 1 plus 0, at an angle, the imaginary part, we just have e to the 0, which is 1 at an angle y. This geometric insight is coming from Tristan Needham's Visual Complex Analysis book. If you are interested in this material, get this book. Yeah, if you're going to get one book, get that book. It's great. Okay, done.